Okay, so without further
Yeah,
ado,
thank you.
it's a pleasure to have Lennart Meyer, who kindly agreed to speak in this seminar series. The title is, well, the title that I wrote down is The Chromatic Behavior of Algebraic K-Theory. Okay, take it away, Lennart.
Yeah, thank you very much for the opportunity to speak here. I guess the title I wrote down is essentially equivalent to the title, which is in the schedule. So, so my basic plan of the talk will be, first, I say some introductory words about algebraic K-theory. Then I say something about chromatic homotopy theory. Then I say something about the interactions. And this will contain the main results. And then at the end, I say a bit about proofs and unstable chromatic homotopy theory, because this will be a main ingredient. And let me see how much I will say about this. So, and please interrupt me at any time with questions. So I think the format should give plenty of time for this. So I'm pretty sure almost all of you have heard some kind of introduction to algebraic K-theory. So, but still, I want to motivate a little bit why one might be interested in something like algebraic theory. And there are many possible motivations. And let me choose one which may be a little bit less standard than some other one might see. So let me give a non-standard definition, which is just for the purposes of this talk. So let R be a ring. A determinant assigns to every invertible matrix M an element determinant of M in a fixed group G, such that two properties. First of all, we want if M and N are the same size, then certainly the product to translate into product determinants. And the second is another well-known property of determinants. If you have a block sum, then you also want to have the product, where of course M and N don't have to be of the same size. Okay, and if R is commutative, the usual determinant, so example, it would be if R is commutative, you can take G to be R cross, and this would be the usual determinant would be an example of a determinant. But as a categorically minded people, we of course want to ask: is there a universal determinant over which every other determinant factors? The claim is the universal determinant is target in GL infinity of R modulo its commutator. So the abelianization of G infinity R. And this is defined to be the first algebraic K group of R. So if R is commutative, we see that in particular it always comes with a map to R cross, but in general there would be more. But even if it's just associative, this makes sense. Let me give a brief proof sketch. So what's the idea? So we immediately recognize that property 1 means that we have group homomorphism from GL and R to G, and also from GL and plus 1 R to G. And we can take an M here and send it to the block sum with identity. And this diagram commutes by property 2. And so we can go to the co-limit and get a determinant here. So GL infinity R is defined as the inductive limit or co-limit of the GL and R. So, and why does it factor over a commutator? So this is a little trick with the block sums. So essentially we can make the argument that the idea is when uses an argument like this. So we determinant of M is the same as of the block sum of M with the number of ones. Determinant of N is the same as the block sum with the number of ones on the other side. And then we can multiply like this. But we can also do it the other way around and get with a similar trick. That's also, so this implies that determinant of M times, sorry, this may be not precisely what I want to say, but let me leave this as an exercise. You can make a little trick with the block sum to see it actually as factors over the commutator. Okay, so this motivates the definition of K1 of R as the recipient of the universal determinant. So, but we not only want to have, as homotopy theorists, we not only want to have a group, we want to have a whole space. So, and one observation is, or kind of classical theorem, is that the commutator in GL infinity R is the maximal perfect subgroup. Meaning the maximal subgroup whose abelianization is trivial. And in homotopy theory, there is a universal way to kill a perfect subgroup. So there is a universal way to kill a perfect subgroup in pi1, or the maximal one in this case, name equivalence plus construction. So it's easy to guess a space. So maybe I should have said this first. So we want a space whose ith homotopy group will be, by definition, Ki of R, but of course it should match the definition of K1 of R we just gave. And what we can do is, so it's very easy to give a space whose pi1 is GL infinity R. And if we apply the plus construction on this, we get that pi1 of this is exactly the K1 of R we had before. So, and the K-theory space, so the K-theory space will be then BGL infinity R plus. But there's a slight caveat, so it's not particularly important for this talk, but you notice that the classifying space of a group is always connected. So pi0 would be trivial, but if you've seen something about K-theory, you know that K0 of a ring should not be trivial. So we just do the most naive thing, then we take the product with K0 of R. Okay, and classic theorem, I'm actually not quite sure due to whom, maybe due to Quill, not due to Siegel. So this deloops to a spectrum which I call K of R. So what this means is that omega infinity K of R is this PGL infinity R plus cos K0 of R. And in particular, we have Ki of R is pi I of K of R. So as I said, you can take this as a definition if you want. Okay, so this is the basic idea of K-theory. So I want to make, and this is really the one we will use in this talk, but I want to make some remarks. So first remark is, you can also define GL infinity R for ring spectrum R. Okay, so when I say ring spectrum, I will mean A infinity ring spectrum, or what's also called an E1 ring spectrum, or strictly associative ring spectrum. So there are many ways to express the same sentiment. So we can define this. And so from this, can also, with a little bit care, we can also define a classifying space and also take the plus construction. And this deloops also to spectrum which might be called K of R. This is the correct K of R if R is connected, i.e. pi I of R is 0 for all I smaller than 0. So e.g. you could take R to be the sphere spectrum or an Einberg lane spectrum and so on, but not, say, complex K-theory. This would be not possible. So you can always do the definition, but it will not have so pleasant properties if it's not connective, and there one would prefer another definition. This is exactly what my other remark is about. So many other constructions of K-theory are possible, and they all agree. And should say again on connective ring spectra. So so e.g. One can do it via group completion. Of BGL and R. So this forms, this guy here forms a monoid under block sum. This is very similar to the spirit we had before for the definition of determinants. And we can define a group completion of this. So another thing would be as an invariant. Or what is called perf of R. So perf of R would mean if we have a discrete ring, we might look at the bounded chain complexes of finitely generated projectives and view this via the if we invert the quasi-isomorphisms, we get an infinity category. This would be one definition. And if R is the ring spectrum, is defined slightly differently. One can define it as the compact object of the module infinity category. And it turns out that in some sense the universal invariant with certain properties of stable infinity categories. So this is another definition of the description of K-theory. This is one of the beauties of K-theory, that there are many different motivations and constructions which all lead to the same object, which I always see as a motivation to study an object. So at this point, are there questions? So this does not seem to be the case. So, so let me come to one of the basic properties of algebraic K-theory, namely that it's very difficult to compute. So I already motivated that we want to compute it because so many different constructions lead to the same thing, but it's actually hard to compute. So you can simplify K-theory in some cases by rationalizing. So for example, Ki of the integers is not known in general, although we know a lot about it. But there's a theorem of Borel which says if we tensor this with Q, we can actually completely compute it. Namely, it's Q in degrees. Just let me check it to not say something wrong. Oh, I think it's degrees 5, 9, 13, and so on, and 0 else. Okay. So I don't want to say very much about the proof, but I want to say one very short ingredient, namely, so we call that omega infinity, KUZ, is Z cross VGL infinity Z plus. Now, it's a general fact about the plus construction that if we have x goes to x plus, induces an iso in every homology theory. In particular, in rational homology. So this means that the rational homology of this infinite loop space, and let me just leave out the Z component. So it's not what I want to write here. It's the same. As of BGL infinity Z without the plus. And Borel shows, or let me make the statement with cohomology, this would be also possible, computes this to be an exterior algebra. So this is a very difficult computation, but you might think, okay, for GL infinity Z is a kind of classical object. I have some techniques to compute something about this. And if you know some basic rational homotopy theory, you see if you have a space whose rational cohomology is an exterior algebra, you know something, you can compute its rational homotopy groups. And the rational homotopy groups of this guy will then be the same as of the infinite loop space of K theory. And so the same as of K theory. Okay. So this tells us as an example of rational computation for a discrete ring, because of a usual ring. So what about ring spectra? So there's a very useful theorem of Balthausen's, which says if R to S is a morphism connective ring spectra, which is a rational equivalence. So the equivalence of rationalized homotopy groups and an ISO on pi 0, then K of R to K of S is a rational equivalence. So when you see a theorem like this, you might ask, oh, is it not maybe true in general that if R to S is a rational equivalence, that the morphism of K-theory spectra is also rational equivalence? So warning, we can look at Fp to 0. So I will have the habit of not distinguishing between a ring and its Algebraic lane spectrum here. So you can also read this as HFP to 0. It's a rational equivalence, but K0 of Fp, this is easy to compute, just the integers. So K of Fp to K of 0, which is 0, is not a rational equivalence. So we really need this isomorphism on pi 0, or at least something along these lines. It cannot be true in complete generality. So, and just let me formulate one corollary, namely, we can look at the morphism from the K-theory of the sphere spectrum, which sounds very complicated to compute, to the K-theory of Z. And we know by Sayre's theorem that the map from S to Z is a rational equivalence. So we see that this is also a rational equivalence. In particular, we know precisely what the rational algebraic K-theory of the sphere spectrum is. And motivation of Walthausen to study this was that he could relate by the stable parametrized H-cobordism theorem knowledge about the K-theory of the sphere spectrum to knowledge about high-dimensional manifolds, particularly their diffeomorphism groups. And so he wanted to know something about this. And this way, one gets powerful bridge transport from the rational information we've just computed into geometric topology. But I'm afraid this won't be the topic of my talk, but rather how to extend this theorem of Walthausen and this partial understanding we have of rational K-theory in some sense to a higher level. And this will be about chromatic homotopy theory. So time is too short to give kind of a complete introduction to chromatic homotopy theory here, but I want to say a few words, particularly to motivate why I see this as a very natural extension of the ideas going into rationalization. So fix a prime P. And work P locally. So implicitly, we have in the following few lines everything localized at P, just to save some notation. So let E be a spectrum. So then rationalization is just the same as inverting P, because we P localized everything. So now I write something which looks a little stupid, namely that E is the same thing up to equivalence as E tensored with a sphere spectrum, where some other people might, what I write here as tensor, might also write as a smash product. So why do I write this? Well, so P, multiplication by P is a non-nilpotent. morphism from the sphere spectrum to the sphere spectrum. And because the maps from the sphere spectrum to sphere spectrum are z-localized at P, we see there are not so many other interesting maps I can take. So I can either take a unit, essentially, or a power of P. So if I want to invert an element, an endomorphism of the sphere spectrum, the only thing essentially I can do is to invert P. But clearly, I've lost a lot of information. For example, if I take the sphere spectrum mod P and I invert P, then it becomes 0. So this I don't want. So I look at the sphere spectrum mod P tensor E, or E mod P if you want, as in some sense an orthogonal process I can do to a spectrum. Okay, but this is not the end of it, because now I can ask, is there a self-map of the sphere spectrum mod P, which is non-nilpotent? So I like to invert. And I have to allow a suspension of the sphere spectrum here, but this can maybe be ignored. So, and actually there is a self-map, which I denote by V1. And in some sense, this is also essentially unique. So I can take powers of V1, but I cannot do much more than that. So I have now two possible things I can do. I can invert V1, or I can quotient out by V1, in the sense, take the cofiber of the map V1 on the sphere spectrum, mod P. Okay, and so this map V1 was already known to atoms, but it's a very non-trivial theorem by Hopkins and Smith that actually this procedure can be extended indefinitely. So, so let me take a definition. Then we define Tn as sphere spectrum mod P mod V1 to Vn minus 1, and then invert Vn. So this, in this language, this would be E tensor T1, and this would be E tensor, yeah, I guess T0 here. Okay. So, and instead, of rational equivalences, we are now interested in Tn equivalences, i.e. maps, say E to F, such that E tensor Tn to F tensor Tn is an equivalence. So here I should make a remark, because the Tn are, even if you've heard about chromatic homotopy theory, are unlikely to be familiar with, you're unlikely familiar with, unless you have been to Thomas' talk he has given a few weeks ago, where he's spoken about this. So there's a cousin of Tn. So there's a cousin of Tn called Morava K theory, Kn. So every Tn equivalence is a Kn equivalence. So this is always true, and that every Kn equivalence is a Tn equivalence. It's the Telescope conjecture. So this is, I think, one can say one of the most important open problems in chromatic homotopy theory besides concrete calculations. But it has been solved in a number of cases. And the most important one is, so this holds in many cases, in particular, if n is 1 or between mu modules. So this would be two important cases where Kn equivalence and Tn equivalence are the same. So if you're a little bit afraid of this Tn but are quite happy about the Kn, I would invite you to replace every time I say Tn this by Kn, and you won't lose a lot of things, especially because many of the interesting applications are actually already at height 1. So when n is 1, where they are the same. It's just for certain technical reasons, I have to use the Tn because else I don't know how to prove a certain state. Okay. So this, I think, is what I wanted to say as a very short introduction to chromatic homotopy theory. So are there questions about that? Okay, so let's continue. Now let's talk about the interactions. Of algebraic K-theory. Of algebraic K-theory and chromatic homotopy theory. So this was started, one can say, by Mitchell and Thomason. And I mean, Walshausen had also a paper about this. So this was already in the 80s and 90s. This was a topic people considered, but today it becomes just much more is known due to more advanced techniques. So one thing I want to say is, so say R is a discrete ring, so not a ring spectrum, but just a usual ring. Then Mitchell has shown that the K-theory of R is Tn acyclic for every n bigger or equal to. So meaning that, so i.e. Tn tensor K of R is 0, or we could also phrase it equivalently as the Tn localization of K of R is 0. So this might be a disappointment because almost all of these are 0. So, and if you have heard the term redshift, this is also related to this, because, so note, if we view R as HR, so I'm a plane spectrum, maybe then it's a fact that Tn of HR is 0 if n is bigger or equal to 1. So we see that we have a shift of exactly 1 between these numbers. And this is, for reasons I don't want to get into right now, it's called a redshift phenomenon. So it's a quite general phenomenon observed in several cases, but not proven in very many cases, that K-theory seems to shift height by 1. And this is, I think, one of the original things where one can observe this. So you might be disappointed. These localizations are almost always 0, but in n equals 1, they're actually quite interesting. So assume that R is commutative. That P is invertible in R, and R is nice. So I don't want to state this precisely, but these are very mild conditions. So we don't ask for regularity or something like this, just very mild conditions I'm talking about. So it's a consequence of the norm residue theorem of Wojewodsky and Rost, plus work of many, many people. So I should certainly name Thomason here. And I think the best treatment of this result, and I think also parts of the proof are only found there, is in a more recent article by Clausen and Matthew. So about étale K-theory, they prove in particular the following result, but I'm not allowed any longer to attribute this also to them because Akil raised some protest last time I did this. So as the following theorem, that if we take the peak completion of the K group, we can map it to pi I LK1 of K of R. So note I switched here to K of 1 instead of T of 1, but this doesn't make a difference because I said above that K1 and T1 equivalents are the same. It's an ISO for I sufficiently large. So in this case, sufficiently large doesn't mean a crazy high thing which we cannot control, but rather it means we have a specific number which I has to bigger than, and for example for R equals Z, I think we just need I is bigger than 0. So it's very mild. And I mean, this is done in several steps, which maybe I should not say much about here, but essentially you relate the right-hand side, so this guy, to what's called étale K-theory, so the étale shiftification of K-theory. And then the second step, you can relate the étale shiftification to K-theory itself using that étale cohomology and motivic cohomology are isomorphic in range, which is the normal residue theorem. I mean, it's a very deep theorem. Okay. But this certainly says that K1 local K-theory is a very interesting gadget. So now it's maybe time to formulate what is the main theorem of this talk. And before I formulate this, let me first recall what Waldhausen proved. So this theorem was, if we have a morphism between connective ring spectra and isomorphism pi 0 and a rational equivalence, it's also rational equivalence on K-theory spectra. And we prove an analog in the world of Tn equivalences. But one has to be a little bit careful how to phrase it. So let's see. So let R to S be an n-connective map. which means that the lowest homotopy group of the fibers in degree n, anthropomorphism of connected ring spectra that is an equivalence in T0 to Tn homology, then the same is true for Kr to Ks. So note that we really have to ask here for all the T0 to Tn. So I don't know of a version of this where I can just say, oh, I just know it's a T15 equivalence, and I want to deduce that the map on K-theory spectra is also T15's equivalence. So I also don't think this will be true, but certainly I don't know how to prove it. So, but there's so note that it's almost, so if n is 0, it almost reduces to, okay, so maybe I should say, maybe I say n should be bigger or equal to 1. So if n is 0, so T0 is then the same as rational homology, so it's almost the same statement as Waldhausen proved. But to be safe side, I say n bigger or equal to 1. So I should also say there is a version where I don't have to use the T0, so can leave out T0, which is the same as the rational homology, if we have an n+1 connected there. Okay,
Hey,
so yes.
This is David Ayala. You said a little bit ago that you're working over a fixed p kind of from that point onward. Could you just say in words how p is involved in the statement of this particular theorem?
Okay, so I should be a little bit more precise here, because I don't want to, so here I don't say anymore that everything is implicitly p localized. So, okay, so R and S don't have to be p local, so this is not necessary. But so this T0 to Tn depend on a fixed prime p. So so this is kind of a bit unfortunate notation, but okay, T0 is independent, it's always HQ, but Tn is certainly dependent on the choice of a prime p.
Certainly. Okay. Thanks.
Okay, so what I should have also said maybe that K1 equivalence is the same as an equivalence in mod P complex K theory, but this may also be confusing because then I have topological K theory in there and algebraic K theory here. So let's do an example. In some sense, this is coming back to exactly the confusion I just wanted to avoid. Namely, say you want to understand the K theory of Morava K theory. So it turns out that Morava K theory is an ring spectrum, so this is good. And say we want to apply the theorem I just phrased to this. So the claim is that Ti tensor, this K-theory, is 0 for all I between 0 and M. Okay. So what is the proof? So I should tell you what the homotopy groups of Km are. So they are given by Fp and Laurent polynomials, where Vm has degree should remember this. Okay, maybe it's not so important. So it has a certain degree which is high enough. So okay, I want to apply the theorem, but there's one problem. Namely, the theorem only applies to connective ring spectra. And whatever degree Vm precisely has, that's positive degree. So the homotopy is all over the place. But I can do a thing, namely I can take lambda Km, which is the connective cover, and as a separate argument, why this thing is a Ti equivalence. This is essentially boiling down that one has a localization sequence where one can identify the fiber with the K-theory of Fp, which one knows to be Ti acyclic. Okay, so then this Km, lambda Km, has homotopy groups of polynomial ring. So now I take R to be K of M, and this maps to HFP, which degree 0. So it turns out that this is a T1 to Tm minus 1 equivalence, because both the source and the target are 0 in T1 to Tm minus 1 homology, as one can show. And then one can also show that this map is as connective as necessary. So we get that this is a T1 to Tm minus 1 equivalence. And turns out if we're just interested in this Ti homology, it doesn't hurt to P complete here. And it's a classic theorem of Quillen that the K-theory of Fp, if we P complete, is just the Eilenberg lane spectrum. So it's just concentrating degree 0 and just a ZP there. It's a very beautiful computation. And we know that this thing here is Ti acyclic for I bigger than 0. So this is a sample computation one can do with this theorem. So it's a much more interesting question, by the way. What happens if the height of T and the height of the Morva K-theory is the same? And I would suspect this is also 0 by some redshift phenomenon, but this is certainly something I don't know how to show and what our theorem does not give. Are there questions about this computation?
Hey, Leonard, this is Aaron. I have two questions, actually. First of all, I'm vaguely recalling that aren't there multiple E1 structures on Morava K-theory? And if so, does this depend on that?
So I recall, I'm not quite sure, that actually there are infinitely many MU algebra structures on Morava K-theory, but maybe they are all equivalent. But actually, this is not relevant. We don't need anything specific about the A infinity structure.
It just has
so
to
it works
have
for any.
a structure. Okay, cool.
Yes.
And then also I was wondering, in the statement of the theorem, you have these conditions on the ring spectra. Can you translate any or all of them into conditions on categories of perfect modules?
So let me see. I mean, that the connective could be translated in that, I mean, then the perfect modules of T structure.
Mm-hmm.
And I mean, I guess the connectivity could be seen as you just look at the tensor unit, and the endomorphisms are essentially.
What tensor unit?
So
these are just ring spectra.
Oh, yes. So there's no tensor unit. So yeah, I'm not sure the connectivity can be so easily translated unless you remember the pointedness, namely that they are pointed by R respectively S.
Interesting.
And yeah, so I'm not sure this is can be easily seen in terms of the categories of perfect modules. And actually, I mean, this is very useful. Of course, it's a very useful perspective to take a look at the categories of perfect modules, and this will be very important if we want to draw consequences. But as we will see later, for the proof of this theorem, it's better to use the plus construction.
Okay, cool. Thank you.
So are there other questions? Okay, so let me draw a few consequences, and for simplicity, I will restrict to the case that we have a discrete ring. So assume that R is discrete. So there are a few. So sorry, maybe I say one thing first. So corollary of the theorem is, so let R be connective. And K1 equaling T1 is cyclic, meaning that if we apply K1 homology, it's trivial. So then the K theory of R to the K theory of pi 0 of R is the K1 equivalence. So this almost follows directly from the remark I've made above here, only that the map is just one connective and not two connective as I would want here, but there's a little trick to go around this, which I certainly don't want to state here. And turns out that just knowing that K theory is truncating, as said, so this is called truncating, because this means that K1 local K theory does not distinguish between, on K1 is cyclic, does not distinguish between connective ring spectrum and its pi 0. Just knowing that K1 local K theory is truncating has a number of formal consequences. So it's a number of formal consequences. Even, and this might be surprising, in the case that R is a usual ring, because being truncating seems to be totally about ring spectra. So the first is that K1 local K theory is what's called Neal invariant, which means that it does not see the difference if we quotient by a nilpotent ideal. So in particular, we have that the K1 local K theory of Z mod P to the N is equivalent K1 local K theory of K of Fp. And we've seen above, I think I phrased it in terms of Ti, but this doesn't make a difference here, that this is 0 here, because this thing is just HCP if we P complete. So this is convenient, and I should say two things about this. First, that this was also shown by Clausen, Matthew, sorry, by Bud, Clausen, and Matthew shortly before we found our result, and it actually was a motivation for us to prove our result, to give another proof of this result. And I should also say, while the K-theory of P was already computed by Quill using the plus construction, actually, the K-theory of Z mod P to the N is still largely mysterious. So while we cannot really compute it group by group, this gives part of a qualitative understanding of this K-theory. So another consequence, which actually follows from one in a non-obvious manner, is that K1 local K-theory, where K1 is also depending on fixed point P, is insensitive to inverting P. So this explains why a little bit above, when I phrased this deep theorem here, I assumed that certainly P must be invertible, because inverting P does not change the right-hand side, but would certainly change the left-hand side. So I really have to assume that P is invertible here. So, and the third thing is that that the K1 local K theory is also what's called homotopy invariant, in the sense that we have a polynomial ring that has the same K theory. So this is known for usual K theory in the regular case, but not in general. So in some sense, the upshot is, so I should also say that these consequences have also been known to Bud, Clausen, and Matthew. So the upshot is that K1 local K theory has many very pleasant properties, but captures a non-trivial amount of algebraic K theory. So this is the upshot of this section. And I should also say that actually just yesterday, Akil Matthew has also given another proof, a third proof of the vanishing of the K1 local K theory of Z mod P to the N. So the original proof by Bud, Clausen, Matthew was using work by Bud and Scholze on prismatic cohomology, which they used to compute TC of this, and they used then Dundas, Goodwill, and McCarthy theorem to compute this. So this is certainly an approach I can say very little about this because I don't understand prismatic cohomology. And Akil has now another approach using another theory called TR, from which he can show vanishing and deduce vanishing then for TC and then for K theory. So there are three very different approaches here, how to show this vanishing. Okay, are there questions about this part?
Hi, this is Shaul.
Hello.
Shaul Volkan. So I have a question. In these consequences, 1, 2, 3, is R a ring spectrum or is it a discrete ring?
So here R is discrete. So parts of this also hold without R being discrete. So okay, actually it's a good question. So for the first one, I find it a little bit hard to really make sense out of this if R is not discrete, because what is a near-potent ideal? I guess you could say something, and so I guess I can say something. One way to say what a near-potent. Another thing in ring spectrum, which might remind us of a near-potent thickening, would be if we have a truncated ring spectrum. So a ring spectrum which is only concentrated in finitely many degrees. And it's also consequent of this corollary above that the K1 log K theory is the same as of its pi 0. So this would be in some sense a derived Neal invariance. And so 2 is also true if R is K1 is cyclic, I think. I think we just need that K1 is cyclic. And 3 is also true in some generality for ring spectra, but I must admit I don't quite recall in which generality.
Thanks.
Yeah, but yeah, this is a good point. And this is actually a strength of our approach because Bud, Klaus, and Matthew can only do this for discrete rings or for HC algebras, while we can go a little bit further with this. Thanks for the question. So are there further questions? Okay, then I want to say a little bit about the proof, not very much, especially because I promised to end at past. So I hope it's part 4 now, proofs. And what I essentially will do is I will explain. So let me go back a little bit. So I had this theorem of Waldhausen's as a motivation. And I give you a short sketch of a proof of Waldhausen theorem because it's a little bit easier to understand because it doesn't have any, especially if you're not familiar with chromatic homotopy theory. And then I will say something about what to modify to get the theorem I proved with Markus and Georg. So just maybe I restate the theorem of Waldhausen here to have it, so to speak, on the board. So R to S, rational equivalence, pi 0 iso, connective. Then we have the K of R, K of S. So rational equivalence. Okay. So there's a key ingredient. So we want to have the following. This has nothing to do with K theory. So we want that omega infinity from spectra to spaces preserves and detects rational homology isomorphisms. Okay. So I said this is something we want. So this is in this form, this is not true. So, but it's nearly true. But it should kind of, from purely, so to speak, categorical perspective, it should be a little bit weird because homology is something which plays well with co-fiber sequences. And okay, in spectra, co-fiber sequence and fiber sequences are essentially the same, but in spaces they certainly are not. And omega infinity is something which plays well with fiber sequences, but not with co-fiber sequences. So there's something non-trivial going on. So what's this non-trivial thing? So first of all, we really should restrict to connective spectra because omega infinity just doesn't see anything about the negative part. So we know that omega infinity preserves and detects pi star, say tensor Q isomorphisms as pi I omega infinity E is just the same as pi I of E. And then we can use the rational whitehead, which says that between connected spaces and I have to throw in something which I explain in a moment, simple spaces. Connect simple spaces, rational homology equivalences, and pi star. So Q isos are the same. So simple means the fundamental groups abelian and acts trivial on higher homotopy groups, and this is always fulfilled in the image of omega infinity. Okay. So it's nearly true. We just have to assume that our spectra are connected so that pi 0 is trivial. Okay, so give me a proof sketch of the theorem. So R to S is assumed to be pi 0 iso plus rational equivalence. So so what we want now is that omega infinity R sorry, let's do it a little bit different. So we want to deduce from this that BGL infinity R to BGL infinity S is H star Q iso. So how do we do this? So I should have given you one step in between, which maybe doesn't fit precisely to what I explained before, but so the step in between is, so this implies it's pi star tensor Q iso, and this implies that because GL infinity R, I didn't tell you, but it's true that this is such an iso, and then this is also true if we shift by 1, taking classifying spaces, and then these spaces are connected so I can apply the Whitehead. Okay. So sorry, this is not very easily readable, but I hope you get the gist of it. Then I use that, I explained this earlier, that actually the maps into the plus construction are also homology isomorphisms. So by 2 out of 3, we see that the map between the plus construction is also homology iso. But these are the same as omega infinity. And to be precise, I should take the one connective cover here. But if you want, you can ignore this. Okay. And then I use that. I know that omega infinity detects rational homology isos, as I just said, and then I can remove this restriction here, essentially using that I know it's a pi 0 isomorphism. So this is the basic proof strategy. So you see that at a crucial moment, we use this ingredient, the rational Whitehead theorem, which is a result in kind of classical algebraic topology. And if you want, you can say an unstable homotopy theory. It's really a result about spaces, not about spectra. And it's real, so there's really a difference. And so let me make a short table. Namely, in unstable homotopy theory, there are essentially 2 kinds of invariants. So there are invariants in unstable homotopy theory. So there are invariants which play well with co-fiber sequences, with suspension spectra, and also with the plus construction. And this is, say, homology, and to be consistent with above, rational homology. So this would be one part here. And there are other ones which play well with fiber sequences. With omega infinity, and this might be, for example, taking homotopy groups, rational homotopy groups. And we just used, very crucially, that these things interact well. And if you've ever followed a course or read a book about, or whatever, about rational homotopy theory, this is really at the core of the subject, that equivalence between these two functors are essentially the same. And if you didn't know this, it would be very hard to show very much about it. And now we want to replace this by Tn equivalences here. So let's put an equivalence here, Tn equivalences. And turns out there's a corresponding guy here, which is called Vn equivalences. And I don't want to say very much about this, but this has been studied by a number of people. I think foremostly, I would really say Bausfield, partially building some earlier work of Mahowold, which was more computationally, as you might guess, and also more recent work, which I want to mention. So there's also work of Bausfield and Kuhn, which is, okay, this is not so recent. And there's also a more recent paper by Gijs, which I really like. Okay, so these are a few things I want to say. Namely, there's an analog Vn equivalence, and one really has to study the relationship between Tn equivalence and Vn equivalences. And luckily, Bausfield did a lot of this, and some other people did as well. And at the end, one ends up with the following theorem. And I just give a few names because there should be more. So Bausfield, certainly it's very crucial, but we also have to use a result by Kameli, Schlank, and Janowski, and some other work as well. So we kind of, in some sense, we pieced together a few things, but I think we didn't really add anything of substance. The work of substance was done by other people, namely omega infinity detects and preserves I guess I think numbers n+1 connective, n+1 connective T0 to Tn equivalences. And actually, it turns out for the detects part, one doesn't need any assumption, essentially. One doesn't need that it's n+1 connective here. And it would be also working when we just work with a single Ti. But the preserves part is the tricky part. I mean, they're both tricky because they use some machinery, like a Bausfield-Kuhn functor, but the preserves part is the trickier part, where we also use the results by Kameli, Schlank, and Janowski. And this is really analog, in some sense, of this consequence of the rational Whitehead theorem we had above. And if you look at the proof sketch I gave for Waldhausen's theorem, you might already think, okay, it's not really special about rational homology. If any other homology theory which plays equally well with omega infinity, I can just do the same proof. And this is essentially what we do. So, then we copy the proof sketch above, but with T0 to Tn equivalences instead of rational homology equivalence. Okay, I think this is everything I want to say about the proof, and I think it's everything I want to say in this talk. So I want to thank you very much for your attention and would like to hear questions.
Thank you for that great, clear talk, Leonard. Are there any questions out there? So Leonard, I was wondering if you have anything to say about versions of your main result, but concerning TC or TR or THH. Namely,
yes.
like the interaction between those functors and these localizations at other Morava-K theories.
Yeah, I can certainly say something about this. So, so maybe I write something. This might be easier. So
Sure,
there's this. So if R is connective. So let me think one moment before I say something wrong. So we have a fiber square. So we have a fiber square like this. So Dundas Goodwillie-McCarthy theorem. And you can actually use this fiber square to deduce from our theorem formally that you can just replace TC in this result. So you can just, the same result is just true if we write TC here. And you can use actually a Dundas Goodwillie-McCarthy theorem to show that's equivalent to prove this for TC and to prove it for K. So this is a funny situation because usually one uses TC to prove things about algebraic K theory. But in this case, we actually can use algebraic K theory to prove something about TC.
Yeah, that is interesting. I see. And
I should say most of the other results I said are also true for TC, but what's not true is this thing here. This is not true for TC. So because actually there we use thing Aaron alluded to that one really likes to work with K theory based on perfect complexes and stable infinity categories. And K theory of stable infinity categories commutes with filtered colimits of stable infinity categories, while TC doesn't. And this enters in the proof at some point, and one can not deduce this for TC.
Well, that's interesting. Did you say that the Clausen-Matthew precursor to your main result used the Dundas Goodwillie-McCarthy theorem? Did I catch that correctly?
Yes. They work completely in the TC world.
Right.
So if they want to use something with K theory, they have to use Dundas Goodwillie-McCarthy.
Great, thanks. Are there any other questions out there?
Hey, Leonard, this is Aaron again. I have another question. This is vague, but do you have, how do you think about maps that are like eventually an equivalence on homotopy in sufficiently high degrees? Like, you could formally invert all of those sorts of maps and consider this sort of localization of the category of spectra or something like that. How does that fit in with anything else? Or I don't know. Do you have any comments on that?
That's a good question because I mean, in the way, at least in the way we phrased our result, I really cannot say anything about this because I always had to demand that my maps are n-connected. And what you're asking, if I understand correctly, is something the opposite. It's just an equivalence in high degrees.
Yeah,
but
I guess you mentioned a different result earlier. I'm trying to remember which. It's just off the screen for I sufficiently large.
But
it just got me thinking about sort of like asymptotic equivalences.
There should be a version. Yeah, so I think our main result should have a version which drops the n-connective, or has maybe completely drops the n-connective. And we can prove it if R and S are KO modules and maps KO linear. We can, KO algebras and maps KO linear. We can actually prove this result without any connectivity. And then I think one might see that what you're saying, that it's equivalence sufficiently high degrees, it should induce an equivalence on localized K-theories, because we know that, I mean, as you certainly alluding to, that equivalence high enough degrees, it's a TI equivalence.
Mm-hmm.
So this is an interesting question.
Okay, any other questions out there?
Can I ask a question?
Please.
It's Shachar Carmeli. So can you explain again where exactly you use the fact that you use the TN localizations and not the KNs?
Let's see. So if I look at my main result, or our main result, this is okay. So I mean, clearly for the output, we could use as well K0 to Kn equivalences, but for the input, we want to have T0 to Tn equivalences. And the reason is that, so let me scroll down. So in this this theorem I mentioned here, that omega infinity detects something about T0 to Tn equivalences, I want to do this in several steps. First of all, I can trace what are Vn periodic homotopy groups and Vn equivalences, and a map of spectra is a Vn equivalence if it is a Tn equivalence, more or less by definition. And furthermore, omega infinity preserves Vn equivalences, essentially also more or less by definition, because they are defined by homotopy groups, and omega infinity preserves homotopy groups. So, and this reduces us to saying something about the relationship between Vn equivalences and Tn equivalences in spaces. And this has been studied very well by Bousfield. What he does usually, maybe he does just never talk about some analog where you have something like you have some kind of Kn version of Vn equivalence, which you can formulate, but I don't think he proves much about this. So, so maybe it just all works for input with Ki things, but we certainly didn't have any kind of sources in Bousfield for this, and this was, I think, the main reason why we stuck with Ti, which usually doesn't matter so much, because most examples where we apply K-theory to are maybe MU modules, MU algebras anyhow.
Okay, thank you.
All right, any other questions? Okay, well, you're each invited to join us in the tea room. I put a link to it in the chat just now. So thanks again, Leonard, for that great and clear talk.
Yeah, welcome.